In this video, we'll look at Lewis structures. When we look at Lewis structures, we first want to start by looking at the Lewis dot symbol. When we're drawing the Lewis dot symbol, what that is, as we briefly saw, is when we draw the element, and then a dot represents the valence electron around that element. So if we look at column 1A, since there's a 1 electron in the s orbital, I draw 1 dot. With the second column, since there's 2 electrons in that s orbital, they get 2 dots. And if we jump over to the next part of the main group elements, with boron, since that has an S2 and a P1, it gets 3 dots. And you can see carbon gets 4, nitrogen 5, oxygen 6, fluorine 7, and our noble gases get 8 dots around them. So each one of these dots represents a valence electron. And you can see the count works. I have 2 electrons in the S and 4 electrons in the P. So that's 6 total. 1, 2, 3, 4, 5, 6. And it doesn't matter which period you're in. These, since we're in period 2, happen to be in the 2s2, 2p4. If we look at period 3 for sulfur, that would be 3s2, 3p4. But there's still 6 valence electrons no matter what. And so looking at these Lewis symbols and bonding, for a metal, the total number of dots for the Lewis symbol is the number of electrons the atom will lose to form a cation. So that lithium, since it had 1 dot, since the lithium had 1 dot, it's going to lose 1 electron to form a lithium with a cation, plus our electron. Or even magnesium. Magnesium, we drew 2 dots around it. With those 2 dots, we know magnesium will lose those 2 electrons to form a magnesium plus 2 charge. For nonmetals, the number of unpaired dots equals the number of electrons the atom will gain to form a cation. Or alternatively, the number of electrons it's going to share to form covalent bonds. So if we think about it, if we look at our oxygen that we talked about, oxygen had 2 unpaired electrons. So that means it can form 2 covalent bonds. So that would be the number it's willing to share to form a covalent bond. So it can give us 2 covalent bonds. Or if you looked at nitrogen, nitrogen was 1, 2, 3, 4, 5. So nitrogen has 3 unpaired electrons, which means it can form 3 covalent bonds. Looking at this, we can use what we call the octet rule. The octet rule states that when an atom bonds, they're going to gain or lose electrons or share electrons to obtain 8 outer electrons or 8 valence electrons, or alternatively 2 for hydrogen and lithium. But most other atoms will want to form 8 valence electrons around them. The 8 valence electrons we know is our noble gas configuration. So we can see why the noble gas configuration has been playing such a big part. Noble gas configuration means we filled up that outer shell, which is a more stable configuration for our atoms. Looking in a little more detail at this octet rule. So when we're forming compounds, they're going to add or subtract electrons to get to the 8 valence. That's our octet rule. 8 valence electrons means we have our noble gas configuration, or we filled up a complete shell. Now this works really well for row 2. Specifically, carbon, nitrogen, oxygen, and fluorine. These 4 atoms here follow the octet rule exactly. They want to get 8 electrons around them, no more, no less. Other atoms we'll see in a minute, but these 4 follow the octet rule exactly. They do not have exceptions for the octet rule. So now we're going to use the octet rule to start drawing our Lewis structures, or start drawing what the structures of our covalent compounds look like. When we draw structures of our covalent compounds, we're drawing what we call Lewis structures. Lewis structures represent the molecules and show all the electrons that are bonding and non-bonding. So if I start with chlorine, each chlorine here, if I draw its Lewis symbol, has 7 electrons around it. With the 7 electrons around it, if they share their unpaired electrons, so if these electrons become shared, then they end up with 8 electrons around them. So we see we have 8 electrons in each circle. We can either draw it as circles like this and draw dots all over the place, or we draw a line to represent the 2 dots. So the 2 dots here, same thing as drawing a line between the 2 atoms, which means this line can really just be drawn as 2 dots if you really, really want. So the ones in red, those are the shared electrons, and then all the black dots, those are the non-shared electrons, or what we call the non-bonding electrons. So all of those are non-bonding. And that's because they're not participating in any bonds right now. Only this red one, that pair is considered the bonding electrons. And you can see electrons always come in pairs because we know we can have 2 electrons per orbital. 1 electron pointing up, 1 electron pointing down. So that's another reason our electrons always come as pairs. And so what if we're drawing a Lewis structure for something a little more complicated than 2 atoms? If we're drawing it for something a little more complicated than just 2 atoms, we want to draw our Lewis structure. There's some steps we want to follow. First, we want to find the sum of all the valence electrons for our molecule or polyatomic ion. If it's an ion, polyatomic ion, and it's an anion, then I'm going to add 1 electron for each negative charge. So if I had something like a nitrate, remember nitrate has a -1 charge, I'm going to add up the valence electrons for nitrogen and oxygens and then add 1 electron. So I'm going to add 1 electron to the valence count. Or if we had something like a sulfate, sulfate is -2. Since it's -2, I want to add 2 electrons to the valence count. If it's a cation, then you subtract an electron. So example of a cation, if we had ammonium, since it's a +1 charge, I'm going to subtract 1 electron from the valence count. So keeping this in mind, phosphorus is right under nitrogen, so it has 5 valence electrons. Chlorines, each chlorine is in the halogen category, so it has 7 valence electrons. So when you add all that up, we end up with 26 valence electrons for phosphorus trichloride. So now once we know the number of valence electrons, we know how much we have to work with. This gives us our pool of electrons. So I know I need to use this many total electrons when I draw my structure. So when I draw a structure, first, I'm going to put the least electronegative atom in the middle. So if I look at my electronegativities, phosphorus is less electronegative than chlorine. So phosphorus has to go in the middle. And then I'm going to connect the other atoms by a single bond. So remember, each one of these lines represents 2 electrons. So I'm going to take that 26 and subtract out 6 because I drew 3 lines. And that gives me 20 electrons left. Another strategy, if you're unsure which atom to put in the middle, think about how you draw its Lewis dot symbol. The Lewis dot symbol for phosphorus, 1, 2, 3, 4, 5, has three unpaired electrons. So it most likely wants to form 3 bonds. The Lewis dot symbol for chlorine, 1, 2, 3, 4, 5, 6, 7, has 1 unpaired electron. So it's going to only really want to form 1 bond. So that's another way you can think about figuring out which atom is in the middle. Draw its Lewis dot symbol, and the one that can form more bonds tends to go in the middle. So once we figure out kind of the location of the atoms, and we drew the 1 bond to hold the atoms together, we now want to fill the octets of the outer atoms. Since our outer atoms tend to be more electronegative, we want to fill those octets first. So that's what each one of these dots here, you can see the chlorine now has 8 electrons around each chlorine. So once I filled up the octets of my outer atoms, I only have 2 electrons left for my count. So remember, we want to get to 26 valence electrons total. I've drawn 24 now. And then looking a little bit at my phosphorus. The phosphorus only has 6 electrons around it. It's missing its octet. Since it's missing its octet, I want to draw the last 2 electrons around the phosphorus to fill its octet. So now I filled the octet of my central atom and used up all my electrons. And whenever you draw a Lewis structure, it's always good to double check that everything has its octet and that you drew the correct number of electrons. It's easy to kind of forget a pair or miss a couple electrons when you're drawing Lewis structures. So my next step is, what happens if we run out of electrons? So let's say we're looking at HCN. HCN, I get 1 valence electron for the hydrogen, 4 for the carbon, 5 for the nitrogen. That gives me a total of 10 valence electrons. And we can see here, I've drawn 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've used up all my valence electrons. So that means I have 0 electrons left. But I can see nitrogen has an octet. Hydrogen has its noble gas configuration, has 2. Carbon only has 4 electrons. Carbon doesn't have its octet, but I don't have any other electrons left to use. The only way to fix this is if nitrogen becomes nice enough and shares extra electrons with the carbon. So if nitrogen shares extra electrons, we can form what we call a multiple bond. So what'll happen here is our nitrogen will actually share a couple extra pairs of electrons with the carbon. And you can see between nitrogen and carbon, instead of drawing 1 line, now we've drawn 3 lines. And what that looks like if we draw our dots, so we can see our electron count. 1, 2, 3, 4, 5, 6, nitrogen, 1, 2. So if we draw it out so we can see the electron count, each line, 2 dots, right? Carbon now has 8 electrons around it. Nitrogen still has 8 electrons around it. Hydrogen has its 2 electrons. So you can see when nitrogen shares more electrons, the nitrogen's not actually losing any electrons. Instead, the carbon is gaining enough electrons to get to that octet. So you can really think is the nitrogen and carbon are actually just sharing more electrons. Instead of just sharing 2, now they're sharing 6 between them. And so if you're sharing, just 2 electrons, like we did up here at the top, that's what we call a single bond. If it shares 4 electrons, so I'd draw 2 lines in between, that's what we call a double bond. So with the double bond, they'll actually be sharing 4 electrons total. I draw 2 lines. If it's sharing 6 electrons, like the carbon and nitrogen here, that's what we call a triple bond, because we have 3 lines. Triple. See, the names make sense. And they just let us know kind of how many electrons are being shared between the 2 atoms.